To get a better understanding of spherical coordinates, we're going to sketch the solid described by 1 is less than or equal to rho, which is less than or equal to 2. Another way to put that is rho is between 1 and 2. And phi is between pi over 2 and pi inclusive. Spherical coordinates exclusively refer to points in R3, so I'm going to draw the R3 coordinate planes, coordinate axes, excuse me. Now, rho going from 1 to 2 means we're talking about a radius that goes from 1 to 2, or a distance from the origin that goes from 1 to 2. And so I'll start in R2 in the xy plane with 2 concentric circles that are centered at the origin. One with radius 1 and one with radius 2. Phi is a little bit tricky to understand, but I think we're going to do it here. Phi is the angle made with the positive z-axis. So if phi is equal to pi over 2, that means we're talking about a point that exists in the xy plane. I just shrunk up the inner circle because I wasn't really buying it, but now I feel better about it. Anyway, then phi is to extend down to pi. And if I'm on the positive z-axis, then if phi is pi, then I'm all the way down at the negative z-axis. So we basically have on the outside half a sphere of radius 2. And then on the inside we have half a sphere of radius 1, but that's been cut out. I kind of see this as if eggs were spheres, this is an egg missing its yolk. It's half an egg actually. So we have here, this is the top surface, and then this is just, it's round. Now, what is in these inequalities that's telling me that it should go all the way around in the xy plane? Well, nothing. There's no reference to theta, and so the implication is theta takes on all values that it can, and so theta goes from 0 to 2 pi. Rho goes from 1 to 2. Phi goes from pi over 2 to pi. The fact that we have the back side of this, we think about, well, if phi is going from pi over 2 to pi, then I'm going to land here at the bottom of the z-axis, but I have this frame of reference that tells me that I'm underneath the first quadrant. But phi doesn't really care what quadrant we're in. The quadrant that we're in, or under or above, really comes from theta. We'll see more of how this works as we go, but you should understand that phi has a range essentially of 0 to pi. And by sweeping from 0 to pi, you're going to get the positive part of the z-axis and the negative part of the z-axis. To sweep around circularly in the xy plane, for instance, that requires theta. Now let's move on to the integral in spherical coordinates. It would be a triple integral, of course. And we're going to consider a spherical wedge. Here's our spherical wedge. It's defined by a constant inner radius ρ1 and an outer radius ρ2 that's also constant. A constant smaller angle theta, call it theta 1, and a larger angle theta, call it theta 2. So we'll call this angle here like a delta theta. And a constant smaller angle phi and a constant larger angle phi. That'll give us a delta phi. And then of course for the two radii we end up with a delta rho. I got to be careful with my rho's so they don't end up looking like a p. Now, we need to find the volume of this spherical wedge. The vertical dimension of the outer shell has a value of rho delta phi. Think about this in terms of S is equal to r theta, the arc length formula that you would have seen in trigonometry, with radius rho and angle delta phi. The horizontal dimension of the outer shell is also an arc length, essentially, and it's going to have a value of rho sine phi delta theta. Again, think S is equal to r theta, but recall that in a previous video we saw that r is equal to rho times the sine of phi. Now, you know how this goes. We're going to think of smaller and smaller spherical wedges. And so as this spherical wedge shrinks down, we can really think of it as a rectangular solid, kind of. And so multiplying together delta rho, rho delta phi, and rho sine phi delta theta is going to give us our dv. That is to say that dv in spherical coordinates is rho squared, because we had two factors of rho, times the sine of phi, d rho, d theta, d phi. This is the equivalent for polar or cylindrical coordinates of the r d theta. You know that r you have to remember to bring in. Now what we have to remember is that for spherical coordinates, dv is not d rho d theta d phi, but rho squared sine phi d rho d theta d phi. This leads us to the triple integral. So the triple integral over E of f of x, y, z dv is equal to, folks, this is going to be a lot to write, the integral from c to d of the integral from alpha to beta of the integral from a to b of f of rho cosine theta sine phi, rho sine theta sine phi, rho cosine phi, rho squared sine phi d rho d theta d phi. Folks, this is for constant limits of integration. If we had variable limits, really the variable is only going to show up for the rho variable. Instead of the inner integral, the limits on rho being going from a to b, we'd be looking at g1 of theta phi, g2 of theta phi.